Okay. So the next topic that I want to talk about is an example of something that's bottom-up effective field theory. We've talked about top-down with this example of removing heavy particles. And the classic example of bottom-up is chiral perturbation theory. Or Chiral Lagrangians. So our purposes here are not a full, again, they're not a full exploration of this topic, which is a very large topic. So what are our goals? Bottom-up effective theory example. We will also see in this example the utility of using something that's called the nonlinear realization of asymmetry, nonlinear symmetry representations, and the kind of connection to field redefinitions. Since field redefinitions is something we've been talking about, we'll talk about that. Another thing that this is an example of is an example where loops are not suppressed by the coupling constant. Instead, they're actually suppressed by powers in the power expansion. So that's kind of totally different than what we saw when we were doing integrating out heavy particles, where you just put a loop. You're down by some factor of alpha s, but you're at the same order in the power expansion in 1 over the large scale. This is going to be different. And therefore, in some ways, this has a non-trivial power counting, and more non-trivial anyway than what we were just talking about. So we'd like to give this as an example of non-trivial power counting, and in fact, prove something that's called a power counting theorem. What the power counting theorem means is that ahead of time you should be able to figure out from your effective theory what order various things are. If you draw a diagram, you should know, even before you calculate it, how many powers in the power counting expansion you have. If you didn't know that, you wouldn't know which diagrams to compute and which ones not to compute. You just have to compute them all, and that's, of course, way too much work. So in order to formulate the effective theory, especially since there's an infinite number of diagrams, so in order to formulate the theory, remember, you really have to have power counting under control. And that means you need things like this in order to identify what's leading order. OK, so we'll talk about that. So I'm imagining that maybe like 50% of the class has seen chiral perturbation theory before in some form or another. I know I teach it in quantum field theory 3, so if you took QFT3 with me, you saw a glimpse into it. The things we're going to emphasize here are a bit different, but I am going to assume that you have knowledge of it at some level, and I'll assign you reading if you don't. The other thing I'm going to assume that you have some knowledge of is spontaneous symmetry breaking, because that's not the topic. That's not one of the things that I've listed here. That's not something that I really want to delve into. But of course, if we talk about the Chiral Lagrangian, that's something that comes in particular when we're talking about it from QCD. So I'll remind you of some things that are hopefully familiar, and anything that's unfamiliar you should do additional reading on. So I know that there are some people that are taking QFT3 right now, so this may be something they haven't got to yet, so I will do some review, but for further reading you should see QFT3 or some other source. I've posted some readings on the website. So if we start with QCD, massless QCD, we can divide it into a left-handed part and a right-handed part. And then we can talk about the transformation where we take the left-handed field and transform it by a separate amount than the right-handed field under a unitary transformation, and that's a symmetry of the theory. Now, exactly what symmetry you have depends on how many components you're talking about in this psi field. If I say the psi field is light, then you might think of up and down, and that's one possibility. Or you could throw the strange in there and say, well, the strange is light too, and then you'd have up, down, and strange. And that's just the difference between SU2 and SU3, and both of these are viable choices. So let's make a little table. We have a group, which is the transformations given by the left and the right, and it's going to be broken spontaneously to some other group. So it could be SU3. So there's saying that the left and the right are in an SU3, each of them. And in QCD, that's broken to the vector subgroup. So in this case, the psi would be UDS. And you get Goldstone bosons from that. And there's 8 of them. And that's the pions, the kaon, and the eta. And key thing from our perspective is what is the expansion parameter? And it's not so great because the strange quark mass is not that light. So you can think that the strange quark mass over lambda QCD is maybe something like a third-ish. But you're not really getting better than that. Okay, so there was 8 generations here, 8 generators here, broken to 8 here, and then you have 8 Goldstones. You could do better, but make less predictions if you just considered SU2 and just made the up and down light. Then you just have the pions, and then you just have mu and md over lambda QCD, which is more like a 50th. Okay, so a much better expansion. But then you can't do kaon physics with this because the kaon's not part of the effective theory in that case. So in order to construct a theory for the Goldstones, which are the light degrees of freedom, so we've identified the light degrees of freedom, you'd like to construct an effective theory for them. Those are bound states of the particles in your original theory. And you don't know on pen and paper how to calculate the matching. And that's characteristic of a bottom-up effective theory, that you don't do the matching, that you just start from the bottom up. So in this case, you don't do the matching because it's non-perturbative. So what you do is you say, let's construct the effective field theory based on the fact that I know what the degrees of freedom are, and I know something about symmetry. And in particular, in this case, you know something about symmetry breaking. So one kind of logic is then what you'll get is you'll get coefficients times operators again. The operators will be built out of your pion, kaon, eta fields. And you'll be able to calculate matrix elements of these. But you'll get some coefficients and you don't know the values. So these coefficients you could fit to data because you haven't determined them from some high level theory. You just could fit them to the data and do phenomenology. So it's kind of exactly the opposite from our high energy point of view from the theory with the electroweak Hamiltonian, where we thought the matrix elements were going to be non-perturbative. Here, the matrix elements are something you calculate, and the coefficients are including the non-perturbative physics. You could also get these from the lattice. So a lattice QCD calculation can tell you the values for the C's to use, and then you could just use the Chiral Lagrangian to do phenomenology. Now, because we have this bottom-up point of view, there's something that we don't know, and that is we actually don't know precisely what theory we started with, because all we're encoding about that theory is the symmetry breaking pattern. And so if there's a bunch of upper-level theories that have the same symmetry breaking pattern, they'll look the same. They'll look like they have the same Chiral Lagrangian. And the thing that distinguishes them is that they would have different coefficients, and you wouldn't know that unless you figured out what the coefficients are. So that's another way of just saying that the high-energy physics is being encoded in the coefficients. Okay? So the same Chiral Lagrangian would show up for different high-level theories that had the same symmetry breaking pattern. So this is just one example of Chiral Lagrangians, and we're going to use it as an example, which is perhaps the most familiar, to illustrate our bullets. So one of our bullets was related to nonlinear representations and field redefinitions, so let's start with that one. Problem set's due today. Problem set 2 is posted. So let me talk about something called the linear sigma model. And we'll use this as an example of something that has a symmetry breaking pattern that's similar to the one we want, same as the one we want. And we'll construct from this the Chiral Lagrangian, and since it's the same symmetry breaking pattern, it's also viable Chiral Lagrangian directly for QCD. So what is the linear sigma model? So I'll talk about fields that I call pi without a vector symbol on top. They have two components. One component that's in the diagonal, and then one component, these are polymatrices, in the off diagonal and not fully, and different entries in the sigma 3. So I want to think of this as a kind of full theory. So the full theory for this sigma model is the following. Kinetic term, mass term, interaction term, and I can couple it to something else like a fermion to make it more interesting. With Yukawa couplings. And this theory has an SU2 left cross SU2 right symmetry. Where I take psi left to L psi left, psi right to R psi right, and I also transform pi to L pi R dagger. And if you think of these L's and these R's, you should think of them as something with some generators. So L would have some kind of thing like that with tau left generators, and then some parameters alpha L If I worked infinitesimally in those parameters, then I would if I expanded this out, this would give a linear transformation to the sigma and the pi vector. That's what it's meant for, but it's linear. So a linear infinitesimal transformation to pi and sigma. Okay, so this theory has spontaneous symmetry breaking. And if we write out the potential by taking the traces, then we can write it in a way that makes that obvious by completing the square. And we can always throw away irrelevant constants when we do that. So we get something like that. So the minimum is shifted. And so if we want to shift ourselves over to describe perturbations around that vacuum, then we can do that. So let this guy have a vev, which is, I'll call curly v, squared mu squared over lambda. Pi vector field has no vev, because we want to maintain the vector symmetry. And we talk about a shifted field, which describes perturbations around the vev. We do quantum field theory in the sigma twiddle. And then we write out our Lagrangian in terms of the sigma twiddle just by making a change of variable. And that makes clear who's getting masses when we expand around that vacuum, and who's remaining massless. And of course, the goldstones are remaining massless, and the goldstones, by clever choice of notation, are called pi. See if I can squeeze it all in here. This is something they tell you in Professor 101 never to do, but I'm going to do it anyway. Since if you can't read something, you can always look at my notes when I post them. So I didn't write all the fermion modes down again, but we could do the field redefinition in those modes as well, the shift. In those terms. And the vector subgroup, which remains unbroken, is no transformation for sigma, and the pi field has left equal to right. So we just get some matrix V on both sides. And if we look at the Lagrangian that we have, then we can identify the masses of various things at tree level. And I didn't write down the fermion part, but the fermion gets a mass too from the Yukawa coupling, just like in the standard model. And the pions, of course, remain massless. And the idea of thinking about this as an effective theory is that we can take these to be large. And then there's a clear separation between low energy degrees of freedom and heavy degrees of freedom. So if we want to describe this with an effective theory, we would like to describe the physics of the pions without worrying too much about the sigma and the psi. So we could do that just by thinking about this Lagrangian, but it turns out that you can make field redefinitions and think about using different formulations, which are entirely equivalent, and some of those are more useful than this linear sigma model. So we're thinking here of field redefinitions as an organizational tool. So you'll see what I mean when we go through this. So let's consider some different choices. So there's something called the square root representation. So I just make a field redefinition. Like that, involves a square root. And if I expand it, it starts as sigma twiddle, and then it goes a bunch of other terms. So it's certainly within the realm of the things that are allowed by our field redefinition theorem. And then I also talk about making a field redefinition for the pi as well. And again, this is pi plus other terms. So in this square representation, we're going over to these fields S and psi. So these are our new fields. So we can make that change a variable and just write out our linear sigma model again. And it's the same theory, it's just field redefined. And it looks kind of god-awful, but it's more beautiful than it looks. Okay, so that's something you don't want to do more than once. Okay, so that's one possible way that we could deal with the effective theory is in terms of these variables S and phi. Let me write down a couple other ways, and then we'll talk about which we might pick. So there's something called the exponential representation, also very common. These are very common in the literature, where instead of using S and phi, we use S and sigma. So we take our original fields and we rewrite it as v plus s times sigma. And then we think of sigma as the exponential, and hence the name, of our fundamental Goldstone field. So this is not the same pi. It's some pi prime, if you like, but I'm going to drop the prime. So you write everything in terms of S and sigma, and you keep in mind that inside the sigma is the pi. So the S part at the beginning is the same. And this guy's a little bit nicer to write down. So the S terms that are pure S remain the same. So S cubed, S fourth. since there's no funny square roots in our field redefinition, things are a little simpler. Okay, so that's again, an equivalent version of the sigma model, just using different fields. Everything I can calculate in the original sigma model, I can calculate with these formulations as well. And the final one is going to be different. And that's the nonlinear Chiral Lagrangian. And what I'm going to do to get there is I'm just going to drop the things that have mass from my previous theory, which are S and psi. So I take this exponential representation of the sigma model. These guys are massive. I think about, well, I integrate them out explicitly in this case where we're doing here, which is not QCD. We could do that, just remove them, and that amounts to, at lowest order, just dropping them. And then we have just the thing involving the pion, which is just very simple, that. So this is a viable thing for low energies. The first three actions that we wrote down are identical. They're just field redefined versions of each other. So they're really equivalent theories. And this final one, L chi, is equivalent for low energy phenomenology of the pions. So the first three are actually equivalent to the last one if we restrict ourselves to low energy interactions. So in order to see that, let's do an example where we calculate something. So let's think about calculating pi plus pi 0 goes to pi plus pi 0. So scattering of Goldstone bosons. And Q will be the momentum transfer. So in kind of an obvious notation, it's the difference between the final and the initial, or the initial and the final for the charged guy or the neutral guy. And there's two types of diagrams that can come in. You could have a direct scattering diagram. Or you could have an exchange diagram. So this is pi plus coupling to either the sigma or the S, or depending on which representation we're using. And then the pi 0's down here. And I want to take these and I want to expand. And I'm going to expand in Q squared over V squared. That's going to what I'm going to mean by low energy. V was setting the scale of the masses. So let's see how that works out in the different cases. If I do it in the linear case, then I have both of these types of contributions. This guy just gives me some symmetry factor, which is 2 minus 2I lambda. This guy has a propagator. Square root looks very different. And it turns out in the square root that you can find out that this guy is order q to the 4th, so we won't even write it down. Exponential, this guy is again ditto and ditto. And then I don't have room, but I'll put it up here. In the nonlinear, we don't even have that diagram because we just dropped it. And if I take this line, which is the only one that looks different, I can combine these two terms together. And once I do that, then I realize that this is also giving the same answer. So just rearrange it, put in the relation between mass and coupling and VEV, which looks like that, and expand, and you get IQ squared over V squared as well. Okay, so if I stop at order Q squared, all versions give the same thing. The linear and the square root were equivalent. The linear, the square root, and the exponential are just different versions of the same thing, and all that's changed by making the field redefinition is how I think about these two diagrams. In the linear, the leading order term is not coming from just this diagram, it's also coming from that diagram, and it's actually coming from a cancellation between those diagrams. In the square root and exponential representation, this diagram alone gives the leading order term, and this diagram gives higher order terms, which is kind of what you want if you want to think of these heavy particles as something that is giving higher order corrections. So that can depend on exactly how you formulate it. And from the point of view of just keeping the lowest order degree of the low energy degree of freedom, the nonlinear just gives you immediately the answer from very simple Lagrangian. Of course, it was just the exponential with something dropped. So from the point of view of doing calculations, the linear version here is the one that you don't want to use because there's cancellations between diagrams that you have to figure out. And those cancellations actually affect what you call leading order, because leading order for this calculation is order Q squared. And you don't see that until there's that cancellation that's taken effect. So it's very hard to formulate a power counting for the linear theory for that reason. But for any of these nonlinear theories, we could formulate a power counting, and everything is nice and beautiful. So what happens is that because of chiral symmetry, we have derivative couplings. And in the linear version, we don't see that until we cancel terms. So if you like, if you think about that as a property of the symmetry, you'd like to make it explicit, and the other representations do that. The version that's most convenient is the nonlinear guy, since it's the simplest, and we just think about it, forgetting about the heavy stuff. And it's what we really want for our bottom-up effective theory, because it only has the low energy sigma field, which has the pion in it. And it has the derivative couplings. If you look at how the symmetry works, which I didn't talk about when I wrote down all the different versions, S is for singlet. That's what's behind the name S, so it doesn't transform. Sigma transforms on both sides with an L on the left and a R dagger on the right. And that comes from looking back, noting that S doesn't transform, and looking back at how the pi field transformed. It's just exactly that way. Now, if you write out that sigma, which is transforming linearly, is the exponential of I tau dot pi, and if I put in a convenient normalization, which is the VEV, or this V, then you can work out from this transformation how the pi field transforms, and it transforms nonlinearly. And hence, that's the name for that's where the name comes from. If you do the infinitesimal version of the transformation, and you work it out for the pi a field, which is the 8th component of the vector, a being 1, 2, or 3, part of the transformation is simply a shift, and then there's additional pieces, which are things that you would keep, that are order pi squared and higher. And that's those pi squared and higher terms that, they're saying it's nonlinear. This term here is what's telling you it better be derivatively coupled, because if it's derivatively coupled, if you have a derivative, that kills this constant. Okay? And that was something that was hidden in our linear version of the theory. Now, we've constructed it here from this kind of point of view of integrating out. So I said in QCD we can integrate out, but all we care about is the symmetry breaking pattern. So we wrote down a theory, which is this linear sigma model, had the same symmetry breaking pattern. And we could remove the heavy fields in that, and then the low energy theory, I claim, is the same one that you would use to describe QCD because it's the same symmetry breaking pattern. But that's kind of a roundabout way of getting to where we wanted to go. And you'd really like to just get right to the Chiral Lagrangian from the start. And you can do that. So rather than going through the linear sigma model, we could also just directly get to where we want to go. And here's how you do that. So go back to what the symmetry breaking pattern was, and figure out what is it that we're trying to do with the low energy effective theory. So we have G that's broken to H. The goldstones are transformations in the coset, which is G over H. And we'd like to parameterize them. And what we're doing with this sigma field is we're parameterizing fluctuations that take us around the coset.
I'm a bit confused because
Yeah.
if you don't expand sigma, that Lagrangian has still the full symmetry SU2 left, SU2 right.
Yeah.
But it contains the V,
Right.
the order parameter for the breaking of that symmetry.
Yeah.
So that Lagrangian is representing the unbroken phase?
So I remember I went over to the shifted fields, the sigma twiddle, and then I was expanding around the correct vacuum. I mean the one that's the lowest energy vacuum, not the unbroken.
Okay.
I went from sigma. I originally had sigma. Oh, I should have put, sorry. Thank you. Maybe that. So really when I talk about the linear version, there was two versions of the linear version. There was the original version where I wrote it down in terms of sigma and pi vector, and then I went over to sigma twiddle and pi vector. And when I went over to sigma twiddle, it was just a shift, where I shifted myself to the proper vacuum. So I'm really doing the perturbation theory in the linear here about the proper vacuum. And all the other versions I'm also doing about that proper vacuum, the lowest energy vacuum. So there was a step at the beginning, which is the classic step for spontaneous symmetry breaking, which is, in some sense, just I had to do that to get started when I went from the sigma to the sigma twiddle field. But you should really think about it as the sigma twiddle field as being the field in this linear case. Got a sigma twiddle there. Other questions?